Welcome. In this video, I'm going to talk about how a capacitor is constructed. This will help us to understand some of the variables that go into calculating capacitance. Let's begin. Okay, these two gray bars are to indicate the two plates of a capacitor. You're looking at the edge of the capacitor. So there are the two plates. Let's imagine that we connect this to some kind of battery. So we'll put the symbol for a battery is something like this. We have a long side that's positive, a short side that's the low terminal. So we hook this thing up. You know what's going to happen? The upper plate has to come to the same potential as the high side of the battery. It does that by adding positive charge. Lower plate has to come to the same potential as the low side of the battery. We do that by putting negative charge. I already talked about the details of moving electrons from one plate to another. So this is what's going to happen. So we'll have on the one plate a charge of plus Q, on the other plate charge of minus Q. What's interesting is that if this battery has a voltage of delta V, if you go back, now disconnect the battery. The charge is trapped on those two plates. What will happen? This capacitor will retain the same voltage, delta V, across the two plates because remember we talked about the way those plates obtain the potential is we get the high potential on the one plate by putting positive charge. The low plate gets, the other plate gets the low potential with negative charge. So if we disconnect the battery, the charge is trapped on those plates. You'll have the same change in potential, delta V. Now, that's illustrated here. We have the positive, the negative charge, but here I'm indicating also you'll have electric field present because you have field lines going from positive to negative charge. There's an electric field between those two plates. Now, this field, depending upon the separation between the two plates, can be rather large. Let's take an example. Suppose that this delta V up here was 12 volts. It's not very big voltage, 12 volts. But suppose that the separation between the plates, we're going to call that D. Suppose D is a tenth of millimeter. Tenth of a millimeter. Well, remember, milli stands for 10 to the minus 3. Therefore, this is equal to 0.1 times 10 minus 3 meter. Now we want to calculate what is the electric field between those plates. Remember the formula. If we look at our coordinate system, x, y, so electric field is going to be E sub y. It's in the y direction. So the electric field E sub y. For this capacitor, we have 12 volts divided by this. 0.1. Oh, remember, don't forget there's a negative sign. Negative 12. Negative sign means that field's going to be pointing down. Negative 12, 0.1, 10 minus 3 meter. That will equal negative 12 times 10 to the 4 volt per meter. Okay. And just to emphasize the size of that thing, let's write it out. I have 4 zeros. 120,000 volts per meter. Negative is pointing down. Now, notice a couple of things here. We only started with a 12-volt battery, but because the plates are very close, a tenth of a millimeter, the field is very big because it depends on the delta V over the separation. How close can we put those plates? Well, if those plates get closer and closer, the electric field will get into the range of millions of volts per meter. And at that point, you can reach what's called dielectric breakdown, which means you can get a spark. You can ionize the air between the plates. So you can get a big electric field, even with a small voltage, if those plates get very close. The next thing you should notice is that previously, when we talked about electric field, we said the unit was Newton per Coulomb. Now, we just calculate an electric field that is volt per meter. So, what you find out is that a Newton per Coulomb is the same as a volt per meter. The electric field can be expressed as Newton per Coulomb or volt per meter. It's not obvious that those two ratios are equal, but from the context, when we start with force and we say F equals Q times electric field, it's apparent the electric field is Newton per Coulomb. We start here and we say the electric field is delta V minus delta V over separation. We get volt per meter. They are the same thing. Okay. Now this is we're imagining there's just air between the two plates of the capacitor. Now, by the way, I have a photo over here. This is what capacitors commonly look like. Many years ago, if you open up a radio, they were much larger many years ago, you'd see a device that looked like this. Those metal plates are many plates of capacitor. Instead of just two plates, they combine into many plates, and they're separated by air. It's a variable capacitor because you have a knob there. You can rotate it so the plates overlap more or less. You change the capacitance of this thing. So I don't know how common these are today, if they still exist, but this is what an old capacitor looks like, where you have metal plates, air between them. Okay, so here's an example. Now we say, what would the capacitance of this thing be? Well, remember the formula that the charge equals the capacitance times delta V. So the capacitance of this thing is the charge per the delta V. Now we can consider the relationship between delta V and the electric field because we have E sub y. Let me clean it up some. E sub y equal to minus delta V over delta y. I don't want to get into the positive and negative, so let's go with just a magnitude. Magnitude of this delta V will be equal to magnitude of this EY, delta Y. I don't want to make it look like there's a negative capacitance. So we get a formula something like this. That the capacitance of this thing equal to Q divided by EY delta Y. Okay. So it's more convenient to talk about voltage, but it's going to be useful to consider the electric field. So, and we took a magnitude here, so I can put the bars there. I don't want to confuse the direction of the electric field with capacitance. Capacitance is a number. It's not going to be a negative number. It's going to be a positive number. The charge per voltage. Now let me show you an interesting thing. Curious thing they can do in making this capacitor. Now, this capacitor over here, it's rather large, it's rather heavy, it's hard to keep those plates apart because they're just suspended in air, so to speak. What you'd like to do is make capacitor look like this. Miniature, more capacitance and a smaller volume. You like to put those plates close together. How do you do it? Well, the first thing you have to do is you have to put something between those plates so they're not touching one another. The thing we're going to put between the plates, we'll call, I'm going to switch color here, the dielectric. Dielectric is another name for an insulator. So the dielectric is something we put between the plates. This will hold them together. It will keep them from touching. You don't want them to touch. You want them to hold the charge. And it's an insulator. Now, I've illustrated this dielectric, this material, this yellow stuff in between the two plates. And I've indicated that commonly the molecules that make up any material have dipole moments. They don't have, but if you have different atoms, carbon, hydrogen, carbon, oxygen, oxygen, hydrogen, when you put these together, they can have small dipole moments. So I've illustrated it here. Now these are randomly oriented. Now what I've illustrated on these ovals, which just indicate the molecules that make up the material. If you have any kind of charge separation, just partial charge separation, like from a carbon to an oxygen, or oxygen to a hydrogen. One part can be more negative, one can be more positive, just slightly so. That dipole moment will give rise to a little electric field, which points from the positive end to the negative end, or is typically a portion of a molecule. Positive to a negative portion of a molecule. Now those are random. But what happens when you charge the capacitor? When you charge the capacitor, those molecules are going to tend to line up. So the negative ends are close to the positive plate. The positive ends are close to the negative plate. So look what's happened. You now have two electric fields present. The red one pointing down, call it EY, is from the charged plates. But once you line up all of those molecules, those small internal electric fields are pointing up. So we have another one, put it black, from the dielectric. From the dipole moments of the molecules that make up the dielectric. What's going to happen? One field points down, one field points up. You can get a partial cancellation. You might remember in a previous lecture, in a metal, the charge motion is so significant that the two fields, the internal and the external, will cancel out. You get no field within a conductor. In the dielectric or the insulator, you only get a partial motion of the charge. You only get a partial cancellation of the electric field. So you'll have a smaller electric field. It's not going to be zero the way it is in a conductor. It will be reduced. Let's see what happens to the capacitance. We set up here, this formula, capacitance, the amount of charge divided by EY over delta Y. What we've done now, if you have the same charge on those plates, you have the same separation between the two plates, but you have a smaller electric field, the capacitance will go up. In other words, by putting a dielectric between the two plates, you get a greater capacitance. Remember, capacitance, charge per voltage. So the same voltage, larger capacitance, means you put more charge. What does that mean? It means you can miniaturize things. You can make capacitors smaller by having dielectric in there that polarizes. Now, the degree to which it polarizes. Now, by the way, how does this happen? Well, previous lectures, I said one way it can happen is you can distort the electron cloud, induce a dipole moment. You'll have a smaller factor. A bigger effect would be if you have molecules that can have permanent dipole moments, and they can simply orient themselves in the field. They rotate into position to give you a larger cancellation of the fields. The measure of the ability of the dielectric to polarize and change the electric field is called the dielectric constant. Now, we're going to explore this a little more. Let me just show you the formula for now. Here's the formula for capacitance. Equal sign's missing for some reason. The capacitance is equal to this term kappa. That's the dielectric constant. It's the ability of that material to polarize in the field, and by polarizing in such a way as to oppose the field of the plates, you reduce the overall field. That's the dielectric constant. This next term, epsilon 0, we'll talk about that in the next video. A is the area of the plate, D is the separation. So here's what happens. You want to use a capacitor to store charge. How do you get a large capacitance? Well, you make the plate bigger, it can hold more charge. That's A. You put the plates closer together, because when they're closer, the positive and negative charges stabilize one another. That's the D. Epsilon 0 is just a constant. But the other thing you do to make a large capacitance, find something that has a large ability to polarize, a large kappa. Then you can make a capacitor miniaturize it with a large capacitance. Okay, I'm going to end the video there and come back in another video. We'll use this formula to calculate the value of a capacitor.